In this video, we'll introduce the PLC processor, the brains of the operation, and see how it fits into the picture. This is where we left off in our last lesson, with the input module on the left of our drawing and the output module on the right, and room for the processor between them. With most small micrologic systems, the processor actually is located here in the middle, but with a SLC 500 system, it's usually a plug-in module located in a slot at the left end of the chassis. And also with the PLC 5 system we're using for this lesson, the processor is a plug-in module located in the far left slot of the chassis. But regardless of where the processor is physically mounted in the hardware, we're going to always show it as a box centered right here in the middle of our whiteboard sketch. And we've made it a big box for a reason. This is where the ladder logic program lives, and some other important items too that we'll cover as we move along. Notice that we're only showing one rung right now as an example, not counting the end rung of course. Take a quick look, because we're going to strip out even that rung for a while. We'll come back to it later after we've set the stage for it. One major objective of the boot camp approach is to give you one orderly step-by-step path going from left to right, right through the PLC. And we'll drill you on one problem-solving exercise after another until that pattern becomes second nature. That orderly left-to-right approach will turn out to be a big help when you're troubleshooting the systems back at your plant. So, for the time being, all our program contains is the end rung, and that one can't be deleted. And now that leaves us free to concentrate on other things without being distracted by the program. Now let's go back to switch A and think for a minute. Notice that at this point in the game, there's no way for our processor to know whether switch A out in the field is off or on. We need some type of signal or connection from our input module to our processor. Let's add this little arrow to our sketch. And once the signal gets into the processor, we can't have it just rattling around in there, so we'll add a little box to hold the signal. Believe it or not, this is a very important concept. The little box is called a bit, and the bit box can hold either a 1 or a 0. This should be easy to remember. Bit and box are both three-letter words, and they both start with the letter B. You want to remember that definition. Misusing that little three-letter word accounts for a lot of the misconceptions that people have about PLCs. One big part of the problem is that some of the official books blur the difference between bits and instructions. We'll talk more about that in another video. Now back to the bit for switch A. The PLC contains thousands of little bit boxes. We'll need some method to identify exactly which bit we're talking about. That's what the address does for us. Since this is an input bit with an arrow pointing into the box from the field, it'll usually have an address that begins with the letter I, which naturally stands for input. The rest of the address helps nail down exactly which input bit we're dealing with. Different Allen Bradley platforms use different addressing schemes. So to keep things as simple as possible, we'll assign something like a nickname. It's officially called a symbol, like switch A. Keep in mind that an actual symbol would use an underscore character instead of a dash, but we've decided to use a dash in our videos because it's easier for you to see on the screen. Now let's move over to the output side and do something similar over there. Here we have the contacts for lamp E, but so far our processor has no way to turn the contacts on and off. We need to set up a signal between the processor and the output module. Let's add another little arrow to our sketch. And naturally, we'll need some place inside our processor to store the information for the contacts. Another little bit box will take care of that job for us. And of course, the bit box will need an address to identify it. Since this is an output bit with an arrow pointing from the processor out into the field, the address will probably start with the letter O for output. The rest of the address helps nail down the precise location of the bit. And again, to keep things as flexible as possible, we'll assign the symbol or a nickname lamp E to our new little bit. Keep in mind that in the boot camp class, you'll constantly be working through all of this material on your student workstation, and here's what you'll see on your computer screen. Notice that we've ripped out all of the rungs in the program, except the end rung, of course, and the most important thing right now is that our bits are still actively tied to and from our input and output devices. Just remember that many PLCs have to be in the run mode for this to work. So, when we turn switch A on and off in the field, the bit for switch A located in our PLC processor changes from a 1 to a 0. And when we manually change the 1 and 0 status of our bit for lamp E, the lamp out in the field actually turns on and off. Believe it or not, this simple exercise surprises quite a few experienced students because they've always thought that nothing can happen inside the PLC until they write a program to tell the processor what to do. That's not true. Actually, a lot of things go on behind the scenes of the program, and understanding that behind-the-scenes action is often critical to troubleshooting certain types of problems. So be sure to notice that we don't have any inputs or outputs in our ladder program yet, but even so, the processor is already active and is using the bits to store information to and from the field devices. Now let's go back to the whiteboard and take a more detailed look at what's going on in the background of the PLC. Notice that switch A in the field is open, so there's no current flowing there. And that's why the bit box for switch A contains a 0. Now let's go back to the switch and close it. So now we have an electrical current flowing in the input circuit. And notice that the bit box for switch A now contains a 1. That seems simple enough. But here's one very common misconception that confuses a lot of people. The transfer of information from the switch in the field to the bit box inside the processor does not take place instantly. Yes, it happens very rapidly, usually several hundred times a second, but it does take a certain amount of time. And understanding those timing issues is often the answer to certain beyond beginner types of problems. We'll dig deeper into this subject in our next lessons. Now for the output side of things. Notice that the bit box for lamp E contains a 0 right now, and the contacts for lamp E are open, which means lamp E is off in the field. Suppose we go back to the bit box and manually change the status to a 1. Now we'll see that the contacts for lamp E are closed, and so lamp E in the field comes on. Again, the same type of misconception. The transfer of information from the bit box to the output module is fast, but it does not happen instantly. Once you get past the beginner level of PLCs, a few milliseconds here and there can make a big difference. But the most important thing to keep in mind right now is that all of this transferring of information is taking place hundreds of times each second, even though all we have in our ladder logic program so far is the end rung. No input things and no output things. And now for a quick review. We've got switch A connected to the input module. We've got an arrow to carry the signal from the input module into the processor. We've got a bit box inside the processor to store the status of the input signal. We've got another bit box inside the processor to store the status for the output device. We've got an arrow to carry the signal from the processor over to the output module. We've got a set of contacts inside the output module to control the output device in the field, and all of this fits perfectly into our PLC bootcamp approach of a systematic left-to-right flow of signals through our PLC. And now we're ready for our next lesson.